All right, recording is rolling. Welcome to Tuesday, September 12th. I have a lab lined up for you guys. You guys got it on your desk at page that looks like this on one side and this on the other. It's actually 10 mini labs. Now I'm going to come back and talk about this a little bit, but put that to the side for a moment. Talk about stuff about the class. So you guys know that the first, eighth of the school year ended yesterday, right? Like first general ended yesterday. So you guys turned in your projectile motion puzzles yesterday, right? And that was the last grade that I put in. And all your teachers have to upload grades like here in the next like day, right? So double check focus, make sure you have all your assignments turned in. If you see something that says NTI, that means not turned in. That's counting as a 0, and those are always like huge weights on your grade. Like that could take you down 1 or 2 letter grades right there. That's a great color. So definitely make sure you got everything turned in. Speaking of stuff turned in, you guys' linear motion quiz. Right here, let's look at top scientist again. I'm just gonna make one all video. So this is for my AP students, top scientists. Here's my honor students, top scientists. Period 7. I got this in like because you guys remember we didn't have a period 7 on Friday because of the storm. So so refresh list right there for top scientists for linear motion. Right now, I do want to get you guys' quizzes back soon. I haven't handed them back yet. And there will be a corrections opportunity. So if you guys, whichever problems you missed, because some of you guys did really awesome, some of you guys didn't do so well on the first one, right? Whichever problems that you missed, if you handwrite out how to get to the solution, right? Handwrite out the solutions with the correct answers, because they either circle the correct answers or in the case of graphs, do the graphs for you. And then you staple your corrections to your original quiz and turn those back into the grade tray. Then I'll give you guys a partial credit back. Okay, but I can't hand the quizzes back until I get all of them in, and there's still some late quizzes out there that I'm waiting for. Okay, so I'm still waiting for some late quizzes, so I haven't handed those back yet. Okay, open house is tomorrow, so hope to see some of you guys and your parents here tomorrow. It's 6 o'clock to 8 o'clock. I think there's a form you guys got through your 5th period class where you fill out your schedule, so you know where to go, like what room numbers will be. Okay. And then, guys, what's due on Friday? What's due on Friday? Yeah, projectile motion, take home quiz. There you go. In fact, earlier today, I had some students already turn it in. So, yeah, you can always knock it out early. Okay. All right, so, you guys good so far? Big picture of what's going on in class? All right, so we're going to start the next section really in earnest today with the spring scales lab. Again, this is like 10 mini labs going on. You guys get to work with these spring scales. You guys get to measure forces. A force is very simply just a push or pull. If I push on something or pull on something, I can quantify that not in meters, not in seconds, not in kilograms, but a combination of those units, which is a Newton. Newton is a composite unit. Okay, breaks down into kilogram meter per second squared. That'll make sense here in a few weeks, right? Right. But if I pick something up, right? I can quantify like how much force is that to pick it up, right? I feel there's a weight. There's like a gravitational type force pulling straight down, right? Something like that. Okay. Now, let's take a smaller lab weight. This guy says 500 grams. So that's the mass. Mass is 500 grams. Guys, mass, that's like the amount of material, amount of inertia. Like as I push this back and forth, like that one's a little bit easier than this one. This one's a little bit tougher to change the state of motion, right? If I took these up into the International Space Station where everything's just floating around, would these feel like pretty equivalent? Like how hard it is to change the state of motion? It sure would, even though they would be like weightless, right? They would still have mass, they would still have inertia, it'd be difficult to run back and forth, right? Now, what they wouldn't have floating up in space is like a weight, like a downward force. Now, that's a different concept measured in different units. Right? Speaking of which, let's look at the spring scale. Right? Now, I'm using the brown one here. The brown ones are probably the most useful because they have like a medium stiffness spring constant, right? Go back to the idea here in a minute. Okay? But let me pause this right here, or break this, stop that right there, right? Turn it sideways. Okay? There's actually 2 different readings. There's 2 different scales on these spring scales. Let's get back to where it was. Right, so one side says grams. Guys, grams measures what again? Mass. Right. The other side says capital N for newtons, and newtons measures a force. Right. Now, suppose this was like at 5 newtons. 5 newtons of weight. Right. Okay. Well, it was at the 5 newton part. Right. But on the other side, it says something like 500 grams. Okay. Now, guys, when you're pushing and pulling and you're measuring forces today, when you guys are recording numbers on these tables on your page, okay, do you want to record mass in grams or force in newtons? Which is the correct measurement you guys are making today? Force in newtons. Yeah, I really care about force in newtons. Okay. The mass in grams gets really sketchy. This really only applies to, well, what mass at the surface of Earth and Earth's gravitational field would have generated a weight that would create a force that would stretch it so far. I mean, that's really iffy, right? I really care about force in newtons. That's really all I care about with the spring scales. Okay, force measured in newtons. Right, so you guys are measuring in newtons, not grams, right? The spring scales. Right. If you want to see how many grams of mass it is, you can. There's a number stamped on every one of these. This one says 500 grams. Okay, right. Guys got that? Okay. Right. Now, what's the principle behind this spring scale working? I see if I put some force on it, it's going to stretch. Put more force, it stretches more. Right. So I'm going to do that. Okay. The physics principle behind what makes the spring scale actually works is this right here. It's called Hooke's law. Okay? F equals kx. F, the force measured in newtons, is equal to k times x. X could be how much you either stretch or in some cases compress it, although you aren't really compressing these, you're stretching them. Here's like an unstretched spring right here. Right, so there's some natural length to it. Right, kind of like any one of these. Okay? And maybe some textbook problems, so in the future you might see a compression, but today we really care about stretching. Right. So to stretch it some out, it's going to require some force to do that, right? Right. So, okay, so this is a direct relationship. Like if I put on 3 times the force, guess how much it's going to stretch by? 3 times as much. Or vice versa, you could say to stretch it 3 times as much, you need 3 times the force, right? Oh, that's why this is a straight line right here. That's a direct relationship between the force and the stretch amount. That's it, right? Or force and stretch. Now, some textbooks throw a negative sign on here. So if you suppose you go to college and you open up a textbook that says F equals negative kx, the idea they're getting at is what's called the restoring force. So they say, well, if you stretch it out some amount, the spring is actually pulling back in the opposite direction. I usually don't bother with the negative sign, but if you see that, that's what it's about. Right? Right. Now, what's the deal with that k? That k is called spring constant, which you might know. If you guys remember very first day of school, I gave you guys some papers. One of them looks like this, has all the variables and units that we use in this class. Bam, right there, lowercase k, spring constant. The unit is Newton per meter. Think pretty deeply about that. Yeah, since why that would be the case, right? Look at Hooke's law. Newtons per meter measures the stiffness of a spring. How stiff is a spring? Right? For example, F equals kx. There's Hooke's law right there, right? Which is what we're looking at. Oops, right there, right? Okay. Now, there are different spring scales back there. Say the brown ones are probably the most useful. There's some blue and green ones that if you put a tiny force, it stretches really easy. Oh, look at that little tiny force, it stretches really easy, right? That's hardly stiff at all. Versus like these 3 colors over here, like especially the gold ones, okay? Really stiff springs. Watch this. I pull those. Such a huge force. It's really hard to stretch that. Put all my strength into it. That's a really stiff spring. Huh. How's that translate to like this graph right here? Right? Well, suppose this represents the brown one. It's kind of like the Goldilocks one, right? Okay, they put on some force, it stretches some amount. Okay. Well, those blue and green ones, right, which might be good at measuring maybe the smaller weights, right? That's like would look like this with a real shallow. So that'd be a really small spring constant. Because look at that, I put a tiny force, it stretches real easy. Right. Hey, what do you think the gold one look like on this graph? The gold one's more like up here, right? Stretch with a huge force, right? It only stretches a little bit, right? Because it's so stiff, right? I think that would be like a huge k value, huge slope on this graph. That'd be a huge spring constant, right? You guys kind of get that? Right? So different ones of these might be useful for different applications. The brown is a good default one. Okay, you guys got that? Okay. Let's take a quick glance at this lab. Again, this is like 10 mini labs, right? So I'll help you guys out here. Right, first one, just very simply hang some different lab weights. You guys got a whole box of lab weights here. You pick different ones. Okay? Swap it out, try different ones. And with increasing mass, what does the force look like? What does the weight look like? Got a table, make a graph. Okay. Next one. So this one right here. Suppose you have like one lab weight. Maybe it's this guy right here. Right? And you hang 2 spring scales from it. Right? And then maybe kind of shift them back and forth. Kind of like if you stand on 2 legs, so you can shift your weight from one leg to the other leg. Right? Except this would be a tension example rather than compression, but it's the same idea. Okay? What do the individual readings look like? What do the total readings look like? What is the one rating versus the other rating? What's that graph gonna look like? Right. Then if you take that into 2 dimensions, what if you like spread it out and make like a Y type shape? Ooh, you might have to pull up a protractor so you can measure like exactly how many degrees, right? Spread it out, right? What if you get closer and closer to a T shape, right? Can you ever make a perfect T, right? Got a table, a graph, a couple of questions. One of the questions is, can you make a perfect T shape? Think about that. Right? The chain gang. What if you have scale, weight, scale, weight, scale, weight. How are those scale readings going to look like, right? Or what if you slip an extra one in the middle? That's the next one right here, right? A variation on this, there might be some textbook problems where you see this turned horizontally, right? And maybe there's a train pull like choo choo, right? It's put like a whole line of train cars behind it, right? And say, what's the tension from train car to train car? Right? I wonder what that's gonna look like. Right? On the back, what if you put some motion into this? What if you bob this up and down, accelerate it up and down? Now, accelerating up and down, you guys remember acceleration is a different concept from velocity, so it might get a little tricky as to what direction is what. But think about it. What would an upward accelerating elevator look like? What would a downward accelerating elevator look like? What would it feel like if you're standing inside that elevator, right? Next one. Here's a variation of almost the same idea. What if you attach them with a string and you accelerate this top one horizontally, right, left, right, as it's moving, accelerating one or the other way? What's that going to look like? Right. Oh, it should say here, that string. I always have students every year who don't know how to tie a knot. So let me show you guys faster. Right? Suppose I got the string, because right? Maybe I want to loop a knot on string on that hook right there. Okay, so you guys know like tying your shoes, right? So suppose I go like here, just cross it over like an X shape, right? Then take this and push it through this loop, right? That's like the first step of tying your shoes, right? First step of tying your shoes. And all you do is just repeat that. Right? So then take this, go again, right? Make like another X shape, push it through that loop, right? Pull this. Oops. Let me pause that recording right there. Pause. All right, recording is resume. Record resume. Okay, so if you guys saw do like first step to tie your shoes, just do that a couple times and pull it, and that should make a nice tight knot. You can hook that to spring scales. You can hook that to lab masses if you want. Ooh, look at that, lab weights. Okay, nice knot right there. Okay. Friction. We're gonna do a more expanded version of this sometime next couple weeks. But what if you lift it versus what if you drag it across the surface? What do those two forces look like? And a little question about that. Okay. You may or may not have time to get to these last two. Like, what if you dunk it in water? What does that look like? Okay. And this one is more of a thought experiment. Don't actually do this one; might be a little bit dangerous. But what if you like wheeled it around in a circle, right? Right. And then what kind of circle shape could you make? Maybe you could make a conical shape. Maybe it could be like a vertical circle. Like, again, don't actually do that because it might a little bit dangerous with that. Right? But what do you think? What do you predict? Okay. Now, hold on to this paper today because tomorrow I want to go over all the solutions with you guys, right? And then you can have your work right in front of you, and you can see exactly like did you get what I thought ideally you should get. Okay. Right. So, any questions? Any questions? All right, everything you need is back in the lab area. I will walk back there and help you guys out.